Welcome to Physics Lab 4 Oscillations. In real life, extreme rope sports like rock climbing, rock climbers swing on a climbing rope that stretches. This rope can be treated like a spring because it stretches and changes longitude by using the spring force. In this lab, we will analyze a video that shows a spring mass system. The purpose is to predict the motion of a spring mass system based on Newton's second law, in which the mass swings in an arc while oscillating on the spring, taking into account the forces involved in the motion. Then, the model uses the energy principle to visualize the energies involved in the motion. First, I need to construct the model and analyze the video on Tracker to get the position data points of the motion observed in the video. Then, I created two Python models based on the data obtained from Tracker. The first one uses only Newton's second law to account the forces and predict the motion, and the second one uses Newton's second law and the energy principle to visualize the energies involved in the motion. The results I got showed that the motion predicted by the model is almost equal to the motion observed in the analysis of Tracker. Thus, the model does a good job computing the net force, energy changes, and motion of the mass, directly describing the system and its motion based on Newton's second law and the energy principle. The models use two fundamental principles: Newton's second law to learn about the forces involved and the energy principle to gain additional understanding of the motion. To predict the motion, we need to specify the net force acting on the system by accounting for all significant interactions between the mass and the surroundings. The forces involved are the weight force exerted by Earth on the mass, which is proportional to the mass, and the rope force. Here, I take into account that the rope stretches, so we will model the rope as a spring and treat the rope force as a spring force acting on the mass. It is proportional to the amount of spring stretch. The T period of oscillation used to determine the stiffness and the relaxed length is equal to 1.524, and K, the spring stiffness, is equal to 6.83. These are obtained from video lecture because they are the best approximation to real values. Since at the beginning the system is in static equilibrium, the net force is equal to 0, and the magnitude of the gravitational force is equal to the magnitude of the spring force, and this is used to determine the relaxed length, which is equal to 0.133. With this, I am almost ready to compute the model, but first I need to analyze the video with Tracker. At the beginning of the video, the mass is hanging motionless and then it is released from rest. The length of the string is 0.7 meters, the y-axis is up, and the positive x-axis is right. Start analysis when the motion starts frame 5, and determine points of mass and use the position data in our analysis with the Python model. In the first model, I specify the initial conditions of mass, stiffness, and relaxed length. Delta t is said to be small compared to the time. The system is only the mass. I used Newton's second law to predict the motion, specifying interactions, and the agents interacting are the rope and the earth. So, determines the spring force vector, the L vector, which describes both the length and the orientation of the spring, and it points from the attachment point to the location of the mass. In the motion predicted, the blue arrow represents the spring force, always up, meaning it is always longer than the natural length during the entire motion. The spring force changes in magnitude. The black arrow represents the weight force, always down, and the weight force doesn't change in magnitude. The blue ball shows predicted positions, and the red ball shows observed positions. The second model is based on Newton's second law and the energy principle. The system is said to be the mass, the spring, and the earth, resulting in a change in energy equal to 0, since there are no interactions from the surroundings. This model uses the data values obtained with Tracker. I expect the energy change is equal to 0 because there are no energy transfers from surroundings, since the attachment point shows no displacement. Thus, there is no work done, and the change in energy is equal to the work. In this model, I consider that the mass is negligible, so there are no contributions of the spring neither to kinetic energy change nor to gravitational potential energy change. The model needs the initial values of energies, and after computing the velocity and position of the mass, we can compute the final values of the energies and the energy changes. The graph shows the energy flow, showing the changing kinetic energy in blue, the changing spring potential energy in red, the changing gravitational potential energy in green, and the sum of the energy changes in yellow. The spring potential energy change and the gravitational potential energy change oscillate with almost the same period as the position of the mass of the spring changes, but they are not symmetrical. They are opposite in phase, so when one increases, the other one decreases, and vice versa. Also, the kinetic energy oscillates, meaning that the system gains and loses kinetic energy as the position of the mass changes, but it changes faster than the potential energy changes. In the comparison graphs, the red line shows where the mass is observed to be, and the blue line shows where the mass is predicted to be. As you can see, both are almost identical, proving that the models do a good prediction of the motion of the system. The energy principle is satisfied in my model system because even though the energy changes are not symmetric, the change in total energy is equal to 0, as you can see in the graph line in the yellow. Using the data obtained from Tracker, I determined an estimated period of oscillation from the Y position data and the X position data. As you can see in the graphs, the time period of the motion in the X-axis is smaller than the one of the motion in the Y-axis, meaning that the change in position in the X-axis is faster. Thank you.